All right, section 2.8 is an application of derivatives. It's actually called the mean value theorem. We've had another theorem that had a similar title. Do you remember the title of that one? Intermediate value theorem. Sometimes people confuse the two. They are different. But this one's called the mean value theorem. And before we actually get into the one that's called the mean value theorem, we're going to do sort of a specific example or case of the mean value theorem, and it's called Rolle's theorem. Rolle's theorem says the following. Suppose you have a continuous, we've talked about that word before, differentiable, that means you can take the derivative, function. And it's continuous and differentiable on these interval a to b. And f of a is equal to f of b. Then what Rolle's theorem says is that there is a location between a and b where there's a derivative of 0. Okay, so let's go through the conditions here. I'm going to set up a picture to kind of give us some kind of visual convincing of the fact. I have a point A and I have a point B here. And according to the conditions, f of A is equal to f of B. I also know that I've got to be continuous. That means I sort of, one of the loose ways of describing this is I can't pick up my pen. Once I start with the point A, I'm going to have to continue until I pass through point B, right? And there's no sharp turns, no vertical asymptotes, no holes in graphs, things like that. That's what the continuous part's telling me. So I'm going to draw something that's going to be nice and smooth and connected. And I have to start and end at the same y value. Remember f of A, f of B, those are the y values at those points. So here is the f of A or f of B, whichever one you want to call it. It's the same location, that y value height. So what that's telling me is that right here I have a point, and right here I have a point. And I need to connect those 2 points in a smooth, nice way. Okay? So what are some ways I could connect them? Could do just a horizontal line, right? If I do a horizontal line, is it true that the slope somewhere in between them is 0? Yeah, actually it means the slope everywhere is 0, right? But if I don't connect them in a smooth way, it'll still work. I mean, in a horizontal line, it'll still work. So imagine that I decide I'm going to go an increasing graph first. Well, eventually what's going to happen? It's going to have to come back down because it's got to meet up over here with this particular point, right? So one option might be that it looks something like this. Okay, so do you see a place where it has a derivative of 0? Yeah, I've kind of drawn mine so that it looks like it's halfway. Remember, derivative of 0 means that I've got a location where I've got a horizontal tangent line. And that means often we've got things like peaks and valleys in graphs. So this location right here would have that horizontal tangent line, which has that slope or that derivative as 0. And there's no other way that I could draw it that would fail, unless it failed to be continuous or differentiable, which is part of the conditions that it's supposed to have, right? Okay, so this is Rolle's theorem. Rolle's theorem has this issue where I've got the A and the B at the same location. So now we're going to take Rolle's theorem and we're going to make it just a little more generalized, and we're going to actually look at the mean value theorem. The first part of this looks exactly the same. It says the function has to be continuous. The function has to be differentiable. So all that part's the same. What do you notice it does not have that the previous theorem did? Yeah, well, we'll get to the slope of 0 part. It's before that. Jen was trying to tell us. Yeah, and Josh too. Yeah, it does not have the thing where it said f of A equals f of B. You guys see that? It's just not there. So when I'm drawing my picture, I'm going to draw a picture where they're not. I mean, it doesn't say they can't be the same, but they don't have to be the same. So I'm going to draw a picture where they're not so that we can see how this theorem generalizes the conditions that I had before, the results that I had before. So now I'm going to do f of A right here, and I'll do f of B right here. And there's absolutely nothing that says that f of B has to be above f of A. That's not an appropriate conclusion just because I drew it that way. Okay, so it starts one place and it potentially ends some other height. And somehow this is connected, right? It is connected in a smooth way. differentiable, it is continuous, and so I need to connect the A to the B, and it can be connected in any fashion. So we'll just draw it connected like this because we have a choice. This is what I chose. Maybe yours is connected with a straight line. Maybe yours is connected with a curve that is steeper at the beginning and levels off towards the higher value. It doesn't matter, okay? Here's what this theorem says. This theorem says that there's a location C. I didn't even mark mine over here. I should have done that. This is C, where they're referring to over here. But the conditions that I'm on right now, there is a location C where I've got this weird thing going on. So let's actually look at the right-hand side of this first and see if you recognize this formula. Do you recognize what that formula is? It is slope. It's really just y2 minus y1 over x2 minus x1. It's just the slope. It's the slope between which points? A f of A and B f of B, right? So this slope that I've kind of boxed in blue is the slope of this line right here. And it has a specific slope. Agreed? It's constant. This is a line. It's got a slope. This is right here, this piece. So what does this piece say over here? Well, it says something about the derivative at C. It says the derivative at C should be the same as the slope value that I would just be able to calculate if I used those particular ordered pairs. So I'm going to draw the diagram to show you what it looks like, and depending on the function that you're working with, we'll do an example with function notation in a moment with specific equation. On this particular line, the location looks to be about right here for C. Remember, derivative means slope of tangent line. So if I have this point C, and if I draw a tangent line to it, what this theorem is telling me is that I should have a location, and mine's not perfect, but I should have a location where the slope of my tangent line is the same as the slope of that other line I drew. And if I screwed up and said it was one location where the slopes were not the same, then I would be able to see that because my lines would actually be not parallel, right? The slopes are the same, the lines are parallel. And so I'd say, okay, well, that wasn't the location, it was somewhere else. And there's always going to be a location between A and B where I have the ability to draw this other tangent line that is the same slope as the slope itself for the value between A and B. Now, let's actually talk about how this is the same thing as Rolle's theorem, or I should say how Rolle's theorem is just a specific case of this one. What would happen right here in the formula that I've got boxed in blue if the f of A and the f of B value were the same? It would equal 0, wouldn't it? Over here, where it told you that f of A is equal to f of B, what do you see on the right-hand side of the equation that's the result at the end? Slope is 0. So this over here, really, Rolle's theorem is just a piece of this. If I have f of A equal to f of B, I'm going to end up with a graph that looks like the other one, where I have a slope of 0. Okay? All right, let's actually do an example so that you can see how this actually works in practice. All right, the directions say to check the hypothesis of Rolle's theorem. There are 3 conditions in the hypothesis that we have to check, okay? So we will look at those as we check this. We're going to check the hypothesis of the Rolle's theorem and the mean value theorem. And we're going to find the value of C that makes the appropriate conclusion true. And then we're going to justify that with a graph, illustrate it with a graph. Okay, so let's go back to the conditions. What were the conditions that the 2 theorems have in common? Fantastic. Okay, continuous. And differentiable. We will have to check those conditions. Okay? What is the other condition that we would have to check for one or the other of the theorems? There's one more possible condition to check. What's the third condition inside of the Rolle's theorem? Okay, so that is the third condition that we're going to check. We're going to find out if f of A is equal to f of b. And if it is, then which theorem is it going to be? Rolle's theorem, right, which is just a specific application of the mean value theorem. And if it's not, then it's going to be the mean value theorem. Okay, so these are the things we're going to check. All right, so taking a look at this function, f of x equals x squared plus 1. Is this function continuous? Yes, it is. Is it differentiable? Yes, it is. But we need to justify why we know that's the case. Do you know why? We have theorems that told us this somewhere along the way. You don't need the specific theorem, but there is a theorem that says something that pertains to this kind of an equation. Polynomial. This is a polynomial, right? Specifically, it's a quadratic, like a parabola, but this is a polynomial. Polynomials are always continuous, and they are always differentiable. And we've had a theorem back in Chapter 1 about continuity, about that, and then we've had a theorem in Chapter 2 about the differentiation of that. So these are both continuous, and the reason is because it's a polynomial. You have to check this condition. And the way that you tell me that you've checked it is by writing down this statement. It's continuous because it's a polynomial. It's differentiable because it's a polynomial. How do I check the next part? F of b equals f of a. Well, maybe I should stop for a second and ask a different question. What are a and b in this problem? The -2 and the 2. So in this particular problem, I'm not going to have the a and the b here. I'll put my actual values in so that it works for what we've got. I want to see if f of -2 equals f of 2, right? That's what I really want to check. How do I check? What is f of -2? What do I do?
Plug it in.
Plug it into what? All right, what am I plugging in and where? Okay, I'm plugging the -2 in for x, right? So this is -2 squared plus 1 on the left, and I'm trying to see if this is equal. This is like a question mark equal in the middle. And I'm plugging in +2 squared plus 1 on the right. All right, so what is -2 squared? Plus 1? 5. How about +2 squared? Plus 1? 5. So these are, in fact, equal. Since they are equal, or because they are equal, what does that tell me? Yeah, you're already telling me what Rolle's theorem says. It tells me that Rolle's theorem is what I'm going to use. And Allison's exactly right. Rolle's theorem tells us something very specific. So this is Rolle's theorem. And so Rolle's theorem says there exists a value c between, actually let me write it this way. I'll use -2 is less than or equal to c is less than 2. It's between these, right? There's a c value between -2 and 2. Where what happens? What's going to happen at this particular c value? The slope of the tangent line, right, is 0. So the slope of the tangent line, or we call it the derivative, is actually equal to 0. So we're actually looking now. We know that c value exists. We know that c value is between -2 and 2, and we're trying to find that c value. So what would I have to do to actually find the location where f prime of c equals 0? I've got a function, x squared plus 1. We're going to graph it in a minute. Before we graph it, we're going to do something different, though. Take the derivative. Is that what you said, Steve? Spencer? Who said it? All right, Cooper said it. It was this direction, but you guys are all in this direction. Okay, so we need to take a derivative. That's what this notation says, right? It says derivative. It means slope of tangent line, too, but the notation also says derivative. And we've got a function for which we can do that. So we're going to find the derivative of our function. So what is f prime of x for this function? 2x. That's an easy one, right, Mackenzie? Yes, we like that one. You're like, why couldn't they all been like that on that quiz, right? Yeah. All right, f prime of x is equal to 2x. And this says that I should have a location where f prime of my c value equals 0. So I'm going to take this prime notation, this derivative notation, I'm going to set it equal to 0, and I'm going to solve. Where in the world is 2x equal to 0? When x is equal to 0. So this is the c value that I'm looking for. Not because it's 0, but because it's the value where when I plug it into the derivative, I get 0. They happen to both be 0 here, which is sort of looks funny, but I think I've got another example where they're not. So this is what I've got. Let me see about the way the directions asked it actually above. Let's take a look. It says to find the value of c that makes the appropriate conclusion true, which we did. C is actually equal to 0. And then it says to illustrate the conclusion with a graph. That's where we were, and that's what you wanted to look at too, right, Josh? Yeah. Taking a look at that particular part of this. So here's my solution right here. And then I need a graph. What in the world does this graph look like? A parabola. What else, Cooper? All right, so it has a y-intercept of 1, like right here. How's it open? Up. And if you had something more complicated or you weren't sure or you wanted to verify, what could you do? Plug it in your calculator, right? All right, so over here is my negative 2 value. Over here is my positive 2 value. And if we take a look, they're both supposed to be at the same y value of 5. So we'll mark that there. So there's 5. And sure enough, if you were to connect them with a line, that would be a slope of 0, right? And the c value that we're finding right here is the c value at x equal to 0 right there. And does that, in fact, have a horizontal tangent line? Yes, it does. Because the minimum point of a parabola, right? This is what we get. Maybe I'll do it in a different color. Let's use the blue. So I have that horizontal tangent line right there at the value of x equals 0, or c in this case is equal to 0. Any questions on that one? Okay, we're going to do another one. Same directions. Check the hypothesis of Rolle's theorem, the mean value theorem, find a c value that makes this true, but I get to deal with a sine function. It's trig. All the same conditions at the beginning apply, so I need to check those. The first thing I want to check is I want to check that it's continuous. Second I check is that it's differentiable. And the third thing I check is whether or not the endpoints, f of 0, and at pi over 2 have the same y value. Good so far? All right. Is this continuous? Yes. Is this differentiable? Yes. Why? It's not just trig, it's sine. Not all trig functions are continuous, right? Tell me one trig function that's not continuous. Something from trig. What is that one? Jacob, secant will work. It's not the one you're drawing, but secant is not continuous. Secant has the ones that look like a U shape up and then U shape down, then up and then down and up. And cosecant does that as well. What's the one that looks like Jacob was drawing? Tangent. Tangent and cotangent have also discontinuities. So we don't want to say just trig functions, Josh, because there's plenty of trig functions that don't work. But it's because specifically it's sine or cosine. Both of those do work. Okay, so this is continuous. It is differentiable. And it's because it's a sine function. Yep. And again, we were talking about continuity of the sine function in Chapter 1. We talk about the differentiability in Chapter 2. And both of those things we get kind of for free because it's a sine function. We've already done the work that establishes that it has those features. All right, now we're going to check f of 0 and f of pi over 2. So what in the world do I do to find f of 0? Sine of 0. And I need to check sine of pi over 2, right? And this is where I'm finding out, are these in fact equal? What is the sine of 0? 0, good. What is the sine of pi over 2? 1. And that's a big fat no, right? Those are not equal. So since those are not equal, what theorem are we going to use? Yeah. We have the mean value theorem, and I'll abbreviate MVT. It's the most valuable theorem. No, it's the mean value theorem.
So do you
Yes.
have to write all that out?
Yes, I do.
Okay.
That's what shows that you've checked the conditions. Good question. So this is the mean value theorem. So what does the mean value theorem say? Okay, so first, so there exists, right?
At least it's not blue screen.
Right? Yes. Okay. So there exists C, and it's between the 0 and the pi over 2. So 0 is less than or equal to C is less than or equal to pi over 2. Such that, and this is where some of you were already wanting to tell me before, f prime of C, right, is equal to, and then here's your f of B, minus f of A over B minus A. Okay, this problem with mean value theorem has a little bit more work to it than the Rolle's theorem, because the right-hand side's not 0. It's actually a formula that we're going to have to calculate something with, right? Okay, the left-hand side's still derivative, and so we're still going to do the left-hand side the same way. So let's actually find the left-hand side. We might as well first. Our left-hand side, what is f prime of our function x? Cosine x. Okay, so we'll come back to that in a minute, but that's the left-hand side. The right-hand side, I'm going to switch to the next screen just because I need a little bit more space to write. Says that I'm supposed to be finding f of b. What was my b value? Pi over 2, good. Minus f of a. What was my a value? 0. Over my b value minus my a value. And we've actually found all of those values. What is f of pi over 2?
1.
Good. What was f of 0? 0. And then on the bottom, well, I might as well just do it, right? It is pi over 2. What do I have on top?
1.
1. And we actually spoke briefly about this in a different context last time. This fraction within a fraction stuff's not especially pretty. What do I have to do to fix the fraction within a fraction? Yeah, so instead of division right here by pi over 2, I'm going to do multiplication by 2 over pi. And so my value is actually, awkwardly enough, 2 over pi. We're not used to seeing it written that way, but that's what it is. So the mean value theorem said that I should have my f prime of c equal to this value. So that's f prime of c that should be equal to the 2 over pi value that I just found, right? What was f prime of c? Cosine. Okay, this is the most in-depth trig that we've done in class right now. I need to solve an equation where it says cosine of x equals to 2 over pi, and 2 over pi is not a unit circle value, so I can't use unit circle kinds of thoughts through that to find the x value. Does anybody remember what you do with trig to find this particular x value? And it should say c, not x, sorry. I'm looking for c, so. What's that? We found it over here. F prime is cosine in this function. It's specific to this function. F prime of x is the cosine of x. So F prime of c is the cosine of c. So that's what we put in on the left, cosine of c. How do I solve for c? What do I do? Has it been too long since trig? What's that? Oh, thank you, Stephen. Yes, it is inverse cosine. Okay, so in your calculator, if you take a look, find where it says cosine. Do you see that this actually says COS, cosine? In some other color above that button, it says cosine with a little -1 beside it. So it looks like this. Like the x looks like an exponent of -1. We are going to take the inverse cosine of both sides. Now you should all be in radian mode. If you're not, I'll show you how to do that in a little bit. But we're taking the inverse cosine. We're not dividing by cosine. Cosine's not a number. You can't divide by it. It's a function. It's like saying, how do I remove a square root? Well, we don't divide by square root. We have to square it, right? The opposite of a square root is a square. Well, the opposite of a cosine is an inverse cosine. In essence, it does eliminate the cosine and the inverse cosine on the left because they are opposite operations, like squaring a square root. And I am just left with c on the left. On the right, your calculator gets to give you an approximation for that. So you hit the inverse cosine button. Usually you mean you have to hit the second button and then cosine. And then you can type in 2 divided by pi. And it should spit out at you a decimal, an irrational number decimal, that we're going to approximate. And we'll approximate it with, let's go with 2 decimals unless it says anything otherwise. I don't have it written in my notes, 2 decimals, but let's go with 2. What does it say? 0.88? Awesome. All right, so it says, the directions over here, to find the appropriate value for c, which we did. And then it says that we're going to illustrate this with a graph, okay? So we found our appropriate c value. And I should have written approximately, because we are estimating here. It's an approximately 0.88. And we're supposed to illustrate this with a graph. All right, so we have some points here. We actually only need the right hand, the top quadrant, quadrant 1 on this. But I knew that sine has a value at the origin, 0, 0. And then over here at pi over 2, I know I'm at a value of 1. So it looks something like that, right? And how are those points connected? What kind of a shape? It's a curve, right? It's not a straight line. It's a curve, and it curves upward, like it goes like this. So the curve on the sine graph itself looks something like that. And of course, that's actually a peak there at pi over 2, and we know that beyond that it goes back down. That's not my point right now, but it does do that. Okay, so this is the graph, but this is not illustrating the mean value theorem yet. I haven't actually illustrated that. So to illustrate the mean value theorem means to actually mark all of the pieces on here that make this make sense. The pi over 2 is about 1.57, just to give us some perspective. So 0.88 is a little more than halfway, right? Right, 0.88 is a little more than half to 1.57. So you're looking at something about right here. So there's my c value. And you're going to draw the lines that correspond to the mean value theorem. So you should have a line that extends through the 2 endpoints. That's the original slope line where we got 2 over pi. And then you should have a point at your 0.88 value, right? And the same line right here. And again, my graph's not perfect and my lines are not, but should be getting parallel lines at those 2 locations. That's illustrating the mean value theorem. All right, there are 2 more theorems inside of this section. But before I leave the mean value theorem, any questions you'd like to ask about it? Any concerns over that last problem? Okay. Theorem 8.2 says the following. If you have a function that is continuous and differentiable, is anybody sick of those 2 descriptions? Will you remember them next Tuesday? Oh, I hope so, Spencer. Hope you'll remember those 2 descriptions because they're important. Continuous and differentiable. And f of x equals 0 has 2 solutions in our interval. So what does a solution look like? What does it mean to have a solution? What's that? Yeah, it has an x equals, I mean, what's going on? Like I've got an x equals value, but where is that x equals value coming from? Maybe let's ask it graphically. What graphically has to happen if I actually have f of x equals 0? Y-intercepts. I'm sorry, x-intercepts. Get the right word in there. X-intercepts. It has to cross the x-axis. Okay? So these are locations where it's crossing the x-axis. That's what that's telling you. So it has two places where it crosses the x-axis. If it has two places where it crosses the x-axis, then it has to have some place in between there where it has a slope of 0. Doesn't that sound an awful lot like what Rolle's theorem already said, just shifted down to being on the x-axis? It does. It's exactly what Rolle's theorem says, but shifted it down. So visually, what this is saying is that if I have a graph that looks something like this, two x-intercepts, that there is some location between those two x-intercepts where I have a slope of 0. Right? Yeah, I mean, how else would it be able to be drawn? It's just Rolle's theorem moved down to the x-axis. Now, it doesn't say that there has to be only one location. There could be more than one. I could have drawn the picture such that it did something like this. And this one is the A value, and this one is the B value. Okay? Or maybe I drew it like the same thing I just did, but like that. So it doesn't actually cross the x-axis more than once, but it still has at least one location, but in this case it has more locations where I have slopes of 0, right? Sure. Okay, so this is theorem 8.2. 8.3 takes that theorem and it generalizes it. This one says I have two solutions. It means I have at least one location where I have a derivative of 0. This theorem, all the conditions at the beginning are the same, continuous, differentiable. But this one says not two solutions, but n solutions. And instead of it being one answer to where the slope is 0, I have n minus 1, one value less. And so let's draw one more picture. I'll draw exactly one more. Where I can't draw n solutions. I will draw several solutions. So you have some sort of a weird graph going on. And in your weird graph, you have, in this case, 1, 2, 3, 4 x-intercepts, correct? 4 x-intercepts. So according to this theorem, how many slopes of 0 are minimum that I have? 3. One less. I have a minimum of 3 places where the slopes are 0. And the way that I've drawn it, there's for sure places at this point, and this point. Those are slopes of 0, right? So those are the 3 that I know for sure that I have. But there is actually more the way that it's been drawn. I actually have slopes of 0 over here as well, right? So I could have more than 3, but I have to have a minimum of 3 according to my theorem. Okay, so we're going to do a couple of examples with this one. First one. Prove that this one has exactly 2 solutions. Okay, well, that's different because the theorems that we just looked at did not say anything about exactly. They said what? At least. So there is going to be something at the end where we have to eliminate the ability to have more. But we are going to first show that they have at least 2 solutions using these theorems. All of these theorems have conditions at the beginning that say we have to check for what? Continuous and differentiability. So continuity and differentiability. So the first thing we're going to do is we're going to write that down, just like on the last ones. Continuous, differentiable. Is it continuous? Yes. Is it differentiable? Yes. Why? Yep, because it's a polynomial. All right, I've got a polynomial, so it is continuous, it is differentiable. That's a good place to start. Go ahead and take your calculator, and we're going to take a look at the equation, just, physically what it sort of looks like on the graph. Go ahead and type in x to the fourth plus 6x squared minus 1. So y equals x to the fourth plus 6x squared minus 1. And I'm just going to sketch a picture of what you're seeing on this screen too so we can all reference it. If you want to just use the standard 10 by 10 window, that'll be sufficient for what we've got going on here. Okay, what does the shape generally roughly look like? A parabola. It's not a parabola. How do I know it's not really a parabola? This has an x to the fourth in it, right? So this is not a parabola, but it has the same sort of look to it. Agreed? How is it opening? Up. Where does it cross the y-axis? -1. So it looks something like this. That's what you're seeing on your screen. Is that a fair assessment? Okay. So how many solutions does it look like it has? Solutions being crosses the x-axis, 2. So this appears to have 2 solutions. It appears to have 2 solutions. Let's take a look at a couple of conditions that are going on, and we can verify a few features. Let's have some space over here. From your screen, let me just ask you, looking at your screen, what would you guess? I don't want you scrolling left and right or anything, but just looking at where your x-axis puts the hash marks, where does it look like would be sort of on the outside of the x-intercepts? I just need an area, which we say that the left-hand side, the right-hand side. I need a boundary. It would be okay for me to use 3, Josh? Just so I use as a whole number, okay? Yeah. Whole number 3. And what else? -3. If I'm going to use 3, might as well use -3. Okay, so let's test what happens at 3 and at -3. And I'm also going to test what happens at 0 because it's obviously beneath the x-axis at those points, right? So in some sense, what I'm doing is I'm saying I've got a value over here at -3 that's above, a value at +3 that's above, and a value at 0 that's below. I'm just locating places where it's on either side is all I'm doing. What value do you get at plugging in -3? I don't have this one written down because you guys picked it, so somebody tell me what you get. What happens when you plug in -3 into x to the fourth plus 6x squared minus 1? Your table will do it. What'd you get, Josh? 134. What happens when you plug in 0? That's -1. And you plug in -3? It's another 134, right? Okay. Why did we do that? Well, remember at the very beginning of the lesson, and I said mean value theorem. We had something that sounded like that a little bit before. Do you remember that? What was the thing that Cooper said that we had that sounded a little bit like it, or it was somebody over here? I think it was Cooper. Intermediate value theorem. Okay, so just a reminder, a refresher, what did the intermediate value theorem say? Well, it said that if I have if it's continuous, that was one of our conditions. We encountered that when you guys did your test. If I have something that's continuous and I have one value that's above the x-axis and one value that's below the x-axis, then it means that somewhere in between those two values it crossed the x-axis, right? This is what I'm using right here. I'm using the intermediate value theorem. So let me actually write down some of those details. By the intermediate value theorem, I'm going to write IVT. We know there is a value and we need to give it a name. Let me just call it A. I don't think I've used A on the problem yet. So a value A, and it's between -3 and 0, right? Where f of A is equal to 0. There is a solution. It has to be. There is definitely a solution between -3 and 0. And a value B between what? 0 and 3. Where f of B equals 0. That's what the intermediate value theorem tells me. However, what the intermediate value theorem does not say is that there might be more places where it crosses the x-axis, right? It just says there's at least 2 places, maybe more. So here's where we have this exactly business going on. We know by the intermediate value theorem we have at least 2 solutions, right? But what we want to do is we want to show that we do not have more. So we're going to do something called a proof by contradiction. It's not really a proof, but we're going to try something where we're kind of contradict what we know is going to happen, and we're going to run into a conflict. Okay? So we're going to make an assumption that we know is going to fail. So we're going to assume there are 3 solutions. Because nothing so far has said for sure we don't. So we're going to pretend like there's 3 and we're going to run into a problem. Okay? Here's how we do that. Take a look back over here at Theorem 8.3. Theorem 8.3 says, if I have n solutions, then I will have n minus 1 places where I have derivatives of 0. So we're in the case right now in this theorem where we are saying we have 3 solutions. We're trying to say that, right? We're trying to say, hey, you know what? It's not really 2 solutions. It's 3. We've got 3 solutions. So if we have 3 solutions, how many places are we going to have with slopes of 0? 2. That's what this theorem says, right? Okay, so that's where we are now. Assume that there are 3 solutions. Then by Theorem 8.3, okay, we would have two locations, or 2 x values, or 2 points, whatever. There's 2 places where f prime of x equals 0. There should be 2 of them. So how can we go about figuring out how many places really have where f of prime? What's that? We're going to take the derivative. All right, so let's do it. Let's find what is f prime of x for our function. This is one you like, right? This is a function that's nice. What's the derivative? 4x cubed plus 12x. How do I solve that? Now we've got algebra going on. Okay. Would it be okay for me to take a 4x out, Allison? Just since I can. If I take a 4x out, what do I have left? X squared plus 3. Now what? Not divide, but...
4x equals 0.
Right. Good. So we're going to set each part equal to 0. Okay, so the first one, 4x is equal to 0. That means x is equal to 0. What happens on the second one? Doesn't work. Why not, Josep?
It can't be minus 3.
Right. if I tried to solve it, I would end up getting, oops, that wasn't cubed, that's squared. X squared is equal to negative 3. And when we square numbers, do we get negatives? Not in the real number system, and we're doing calculus with real numbers. So this does not work. X squared can't be negative 3. So how many solutions did I get to the f prime of x equals 0? 1. That's a problem. But there is only one location where f prime of x equals 0. There wasn't 2. So what failed? I didn't get 2 down here. So what was wrong? There couldn't have been 3 to start with. What was wrong is my assumption. Right? I got a conflict. I got something that showed to be not true when it should have been if the conditions had been met. So, but there's only one location where f prime of x equals 0. Thus, our assumption of 3 locations I was going to write it as f of x equals 0. You could use the word solutions, though, if you'd like to, Allison. The f of x equals 0. I know we've got a lot of notation. I'm not talking about the derivative right now. I talked about the original one. So this phrase right here is the same as the phrase solutions, which would be a little bit better, a little bit more condensed. This assumption is false. Thus, there are exactly 2 solutions. I knew there were at least 2 by the intermediate value theorem. And then I assumed, well, maybe there's another one. And when I made that assumption, I ran into a conflict later on that said, no, that didn't work. It can't have the 3 that you thought it might have. Okay? All right, I think there's one more example. This example we're going to do briefly. We're going to delve into this is almost like a foreshadowing of Chapter 3. Because what we're going to do in this example shows a lot of what's going to happen in Chapter 3. This question asks us to determine whether the function is increasing, decreasing, or neither. So some conditions that we've talked about before. If I have a graph that is increasing, what can you tell me about its slope? The slope of the tangent lines are positive. If the graph is decreasing, what can you tell me about its slopes of tangent lines? They're negative, right? And if you end up having a place where the slope is 0, you have a place where it might have a max or a min, right? At least it flattens out, and maxes and mins commonly happen there. So this is something that we need to keep in mind. Let me just jot those down real quick. So if the f of x graph is increasing, and this is important information because you guys had a section, it was in 3.1, I think, where you do graphs. Do you remember drawing graphs for me? I gave you a graph and you had to draw the slope graph, vaguely. Like 2 weeks ago or something, 3 weeks ago, I don't know when it was. If f of x is increasing, then f prime of x is positive. If f of x is decreasing, then f prime of x is negative. And if f of x has a max or a min, then what is f of prime of x? It's 0. We talked about those back in section 1 of chapter 3. Of chapter 2, sorry. Section 1 of chapter 2. Okay, so here's where we're going to start. We're supposed to be finding out whether it is increasing, decreasing, or neither, potentially. So we're going to do that by finding its derivative. So, again, this is a nice, pretty derivative to find. What is the derivative of this function? 4x cubed plus 4x. Nice. All right, what would we do next? Any thoughts? What's that? Take out of 4x. So factor, right, Snyder?
Yeah.
Yeah. All right, so let's take out of 4x. What would I have left? X squared plus 1. Then what? This almost feels like that last problem I did, doesn't it? Yeah. I'm going to set each one of them equal to 0. The first one actually has a solution, x is equal to 0. The second one, just like we had before, doesn't work, right? There's no solutions out of that. There's only one place where actually I've got the ability that the graph might change directions at 0. So how are we going to check? Well, one way to check is something that you saw happen in algebra, and it's to do a sign chart. So we're just going to do like a number line. We're going to put in the x value where it changes locations on the number line, x value of 0. And we're going to sort of just ask ourselves what happens before 0 and what happens after 0. We're going to test it. So we're just wanting to know what's going on over here. So all I need to do in order to do that is I need to figure out a value in that area. So what kind of a number might I choose if I'm looking at values less than 0? Negative 1's fantastic. And what might I choose if I'm going bigger than 0? 1. I love those values. Now here's the catch. We're going to plug them in somewhere. Where? The original function or the derivative? The derivative. The derivative function is going to give us information about the original graph, but the derivative is what we want. So if I plug in negative 1 into the derivative, and I plug in the value of 1 into the derivative, it's going to spit me out an answer. What do I care about that answer? Yeah, I don't really care what the number is at all. I just care, do I get a positive or do I get a negative? So, check it out. What happens when you put in negative 1? You get a negative. What happens when you put in positive 1? You get a positive. So if you think about this number line that we just created, I would draw a number line and do something like this. It's negative, it's positive. What is a graph's, I'm sorry, let me say it differently. If the derivative is negative, what does that tell us about the graph? What does it tell us about the original function, though? It's decreasing. This graph is going downhill here. What happens if the graph has a positive? It's going uphill. So the graph that the answer to the question about being increasing or decreasing is determined precisely by this particular argument. What this is telling me then is that the graph is decreasing. Where? Oh, there's that notation that we like so much. It's decreasing from negative infinity to 0. And then it is increasing. Where? And all of that work supported that. Could we verify that with the graph? Sure, we could look at the graph and make sure that it actually has those features, right? This question is not trying to get you to actually answer the question of increasing or decreasing. It's trying to get you to understand the relationship between graphs and their derivatives. So it looks like, well, why wouldn't I just look at the graph and answer the question? Well, you can answer the question from the graph, but that's not really the point of them asking the question this way. We're going to be using this kind of information with some other details in Chapter 3, and we'll see more of how that plays in with each other. But one way of deciding this information is by looking at the derivative equation. Okay?